This is a lab lecture video to help us understand what's going on when we do the group 1 separation with the acid insoluble ions, and so that we can understand better the chemistry and the chemical equations that are taking place. Now you will be working with two samples side by side. The first sample is your known. It will have silver, mercury, and lead ions in there because you add them to them. And this way, when you do the test for these, you will know what a positive test looks like for each ion. So this way, in case you get one of those ions for your lab practical, you will know what exactly you're supposed to be doing and what you should see if you have that ion in there. The second sample is your unknown. Your instructor will give you a test tube that contains your unknown. It will contain one group 1 ion, two group 3 ions, and one group 4 ion. So this is your practice for the lab practical, but you'll have twice as many ions in it for the practice lab practical than you will for the practical. So don't forget that once you do the group 1 separation and you get your precipitate out for the group 1 ions, you save the filtrate, which is the liquid, so that you can have the sample ready for your group 3 test. And again, when you do your group 3 test, save the filtrate so you can do the group 4 test with your unknown. So the group separation one, those are the acid insoluble ions. So we're looking at possibly having mercury, silver, and lead in there. The group separation one is used to precipitate out group 1 ions from an unknown solution. Group 1 ions include silver, mercury, and lead. These three ions form a precipitate when hydrochloric acid is added. When group 1 ions are combined with chloride aqueous ions, they form mercury chloride, silver chloride, and lead chloride. And those are all solid precipitates, so notice that the states are given. If a precipitate forms, it can be used for specific test 1, 2, and specific test 3. The filtrate, which is the liquid, is then saved for group separation 2. If no precipitate forms, then group 1 ions are not present. And if it's not present, then you don't have to do the specific test 1, specific test 2, or specific test 3. So here are the chemical equations if you have those ions. So the lead 2 plus ion, which is aqueous, combines with 2 equivalents of the hydrochloric acid aqueous to make the lead chloride solid, so that would be the precipitate, and the 2 proton ions would be left over. And these are the equations for the silver and the equations for the mercury. Now remember, you can write anything that you want in your lab manual. You can have any kind of notes or anything as long as it's handwritten in there. So if you'd like to add these equations to your book, and that way you have them for the lab practical, you're more than welcome to. And this picture here just shows you what you may see if you get a precipitate from your group 1 separation. Now you have to be careful when you're doing your group 1 separation. You do not want to add too much hydrochloric acid, because if you add too much hydrochloric acid, you may form this tetrachloro lead complex or this silver complex with 2 chloroligands. And both of those are anionic species. Charged species typically dissolve well in water, and so your solid may redissolve as these new complex ions. So don't add too much HCl, because you'll actually dissolve up your ions that you thought you were precipitating. So your first step with your group 1 separation, you need to prepare your known or your unknown solution. So for a known solution, add 5 drops of each of the silver nitrate, the lead nitrate, and the mercury nitrate. For your unknown, in a different test tube, use 1 ml of your unknown solution. So take an aliquot of that test tube that your instructor gave you to work with, and save the rest of it in case you lose or break your sample, so you still have some left over. After you prepare your known and unknown solutions, you'll do the precipitate the group 1 ions. So to the solution, add 2 drops of 6 molar HCl, and a white precipitate should form. Mix the solution and centrifuge for 1 minute. Add 1 more drop of 6 molar HCl to complete this precipitation. Mix and centrifuge the solution again for 1 minute. So if no more solid forms when the 3rd drop is added, the precipitation is complete. So if when you add the 3rd drop, you see no more cloudiness in solution, that new cloudiness is being formed, that means you've precipitated all that will be precipitated. But if you do see a cloudiness, that means there's more solid that needs to precipitate out. So you will need to add additional drops of 6 molar HCl until you see no more solid forming. But be careful, remember you don't want to add too much HCl because that may cause the silver and lead to redissolve and interfere with subsequent tests. Now if precipitate does not form, then group 1 ions are not present. You'll then need to separate the filtrate from the precipitate, so you separate the liquid from the solid. So once centrifuged, remove the filtrate, the liquid, from the precipitate, which is the solid. If working with an unknown, be sure to save that liquid for the group 2 separation. But we won't be doing the group 2 ions, we'll be doing the group 3, so you'll save it for the group 3 separation. Then wash the precipitate, so wash the solid. So you're going to get rid of any extra things that may be left on the solid. And you do this by adding 1 ml of cold deionized water to the precipitate and mix. And remember, the DI water is the water in the back of the room with the spring-loaded handle. So you have to twist the knob and hold it open for the water to flow. And you want to use DI water, not tap water, because your tap water sometimes has ions in it and you don't want those ions to interfere. So add 1 ml of cold DI water to the precipitate and mix. Centrifuge the solution for 1 minute. Remove the wash from the precipitate and add it to the filtrate, so add it to the liquid. Then you're going to wash the precipitate 2 more times, but this time do not add any of the washings to the filtrate, just throw them away. Save the precipitate, so the solid, for specific test number 1. After you've completed the group 1 separation, it's time to do the specific test 1 for lead ions. Specific test 1 takes place after the separation of group 1 ions from the unknown sample. When a dilute amount of HCl is added to the test sample of the group 1 separation, lead forms an insoluble chloride, so the lead Cl2. Heating the heterogeneous aqueous mixture causes the lead to dissolve and leaves the mercury and silver chloride solids in the solid phase. None of the group 1 ions are very soluble in water at room temperature, but the solubility constant for lead is larger than the KSP values for silver and mercury chloride salts. This is why heating the solution will dissolve the lead chloride and will allow the lead to be separated from the solid silver and mercury chloride salts. Once the lead chloride is dissolved, the filtrate containing the lead is decanted. So that just means that the liquid is poured off. And a small amount of potassium chromate is added. A yellow precipitate of lead chromate confirms lead. So this is what a positive test looks like for the lead ions. The solid should be bright yellow. If it has an orange tint, then some of the silver chloride solid was likely transferred with the filtrate solution when it was decanted. So the chemical equation for this, the first one is the lead chloride in the solid form. When you add the hot water, you dissolve it to make the lead ion and the 2 chloride ions. And remember, we said that the lead has a much larger solubility constant than the mercury and silver. It still has a very small one. It's not very soluble, but it's much larger than the mercury or the silver. And this is why heating it will cause the lead to dissolve, but heating any mercury or silver, it will still stay in solution because these formation constants are still very, very small compared to the lead. Now, if lead was present and you dissolved it up to make the aqueous lead ions, then you add the chromate to it. So you add the potassium chromate to it, so the chromate ions will then bind with the lead to form lead chromate in the solid. So this would be the balanced chemical equation for this reaction. So your experimental procedure for the specific test 1, so the lead ions, you dissolve the lead ions in hot water, add 2 ml of water to the residue from the group 1 separation, and then you're going to heat to boiling in a water bath while mixing. You then separate the solid and the liquid, allow the precipitate to settle, so withdraw the liquid and save the clear solution for the lead test. Wash the precipitate, add 2 ml of water to the residue again, heat and mix the mixture, then discard the filtrate. So you're going to discard this one when you're heating it again. So you're just basically making sure that any lead ions that you didn't remove the first time, you're going to remove it the second time, but we're just going to throw away this filtrate. Then we're going to repeat step 3, wash the precipitate once more to remove the last traces of lead. Save the residue that's solid that's left behind. You want to save that for a specific test 2 and specific test 3. So in step 6, to the cooled filtrate, you add 3 drops of the potassium chromate, and if you get a yellow precipitate, that means lead chromate is there, so that means lead is one of your ions. So you precipitate the lead 2 plus ion as the bright yellow complex lead chromate. Now remember, if you get an orange color or an orange tint to your yellow solid, that means you have traces of silver ion that may have transferred over, and it will give it a dark orange precipitate. But it should be a nice bright yellow if you have the lead present. Your next test is your specific test 2 for the mercury ions. The residue being tested in specific test 2 may contain silver chloride and or mercury chloride. And the process for confirming the presence of mercury in solution is also the process in which all traces of silver ion are removed. So with this test you do 2 things. You dissolve the silver and you also test for the mercury. And this is accomplished by mixing the residue from specific test 1 with 6 molar ammonia. Within this qualitative mix, 2 intriguing things are happening. Firstly, the silver chloride from specific test 1 will dissolve readily in ammonia as the silver ammonia complex. So there's 2 ammonias bound to this silver to make a linear complex, and it's cation. So it's a cationic charge, so it's positive. So it's things that are charged typically dissolve well in water, so this is very water soluble and it goes into solution. Now the filtrate is saved for specific test 3 because it will contain the silver. And then secondly, what's going on, the presence of mercury will be confirmed by either a dark black or gray precipitate of mercury and mercury ammonium chloride via this ammonium extraction. However, if the precipitate is white rather than the desired black, it may be due to the presence of lead hydroxide. So if you didn't efficiently remove all the lead out in your previous test and you have some lead left over, you may have some lead hydroxide being formed in the specific test tube. And this can easily be tested by adding 6 molar sodium hydroxide, because this will dissolve the lead and it will form this lead complex with 3 hydroxides bound to it. And notice that it is also anionic, so this makes it soluble in water. So the chemical equations that are happening in the specific test 2. So if mercury is present, then the mercury will react with the ammonia to form this mercury amine chloride complex, as well as elemental solid mercury, so this black precipitate. And if silver is present, then the silver chloride is in the solid state. It will combine with the aqueous ammonia to make the silver amine complex, which is cationic. Now this reaction here, this is specific test 2 for mercury. A lot of times that students that have silver will forget to write this chemical equation here, so don't make that mistake if you have silver, because if you have silver you need to write this equation under your specific test 2 when you do the lab practical. Because remember, if any chemical reaction takes place, you have to have a chemical equation that represents that chemical reaction. So here's your experimental procedure for your specific test 2 for the mercury ions. So to the residue from specific test 1, so remember that's the one where we tested out for the lead, it may contain the silver chloride or the mercury chloride in a solid form. You're going to add 10 drops of 6 molar ammonia. And in the back of the room, it won't be labeled as 6 molar ammonia, because when ammonia dissolves in water it forms ammonium hydroxide. So don't look for 6 molar ammonia, you want to look for 6 molar ammonium hydroxide. Because if you get to the practical and you've forgotten this and you keep looking for 6 molar ammonia, your instructor will not be able to tell you that 6 molar ammonia is the same thing as 6 molar ammonium hydroxide. After you've added the 10 drops of the 6 molar ammonium hydroxide, shake the solution vigorously to ensure the dissolution, or to make sure that the silver chloride dissolves to form the silver ammonia complex. Then remove the filtrate, which is a liquid, because this will contain the silver ammonia complex if the silver ion is present. And then you look to see if a black or gray precipitate from the ammonium extraction is present, because if it is, this confirms the presence of mercury. And again, remember, if a precipitate is white rather than dark black or gray, this may be lead hydroxide. if lead is present, so you need to add 6 molar sodium hydroxide. And if that white solid dissolves, then you know that that was lead and it wasn't necessarily your mercury there. So your last test for the group 3 ions is specific test 3, and we're looking to confirm the presence of the silver plus ions. Specific test 3 is the last of the group 1 test. In specific test 2, any silver chloride solid was dissolved using the 6 molar ammonium hydroxide to form the silver amine complex, and this filtrate was saved to test for silver in this specific test 3. So this filtrate contains chloride ions, ammonia, and possibly the silver amine complex. In order to test the filtrate for the presence of silver ions, we reverse the reaction by making the solution acidic using highly concentrated nitric acid. So be careful, do not get the nitric acid on you because it will burn your skin. And if you get it on you, you need to make sure you rinse it off for a very long time underwater and make sure to tell your instructor. Now in the reaction, when we reverse this reaction by making the solution acidic using the highly concentrated nitric acid, this neutralizes the base, so it neutralizes the ammonium hydroxide, and it's going to protonate the ammonia. So I'll show you this in equation 2, so that it can no longer bind a metal ion. This causes the equilibrium in equation 1 to shift to the right to create more free silver ions. And the free silver ions are then complexed by the free chloride ions to form the white silver chloride precipitate. And in terms of solubility and KSP values, silver chloride has a KSP of 1.7 times 10 to the minus 10th, whereas ammonium chloride and ammonium nitrate, both those being the only other possible precipitates of the ions, are considered totally soluble in water. The small solubility constant for silver chloride explains why the silver chloride precipitates out and why we know that if there is any white precipitate, it will be silver chloride. So again, this is what's going on. So in equation 1, you have the silver amine complex, and so it establishes this equilibrium because remember this is the formation of the silver amine if we were writing it in the other direction, but these ligands are labile, they can come on and off, and it establishes an equilibrium. Now if you add an acid to the solution, the acid protonates the ammonia and you have the ammonium that's being formed. And once you have the ammonium being formed, ammonium doesn't have a lone pair, so then it can't react to make this silver amine complex. So when you're protonating the ammonia, you're causing the concentration of the ammonia here in this equation 1 to go down, and this shifts the reaction to the right and it produces more silver plus ions. And when you have more silver plus 1 ions, then it can combine with the chloride to form the silver chloride solid. So this kind of shows the overall reaction. So in this overall reaction, the silver amine complex, so that's a positive 1 charge, and there are chloride ions in solution to balance out that charge. When you add the nitric acid, remember that highly concentrated nitric acid, that nitric acid protonates the ammonia to form ammonium, and the chlorides that are there in solution will then rebind to the silver to make silver chloride solid precipitate. So here are the experimental procedures for the specific test 3 for the silver ions. Acidify the solution. So to the filtrate from specific test 2, add 6 molar nitric acid dropwise until the solution is acidic. So you'll test this using litmus paper. And the silver chloride will precipitate if silver ions are present and the solution is acidic. So that ends our discussion of what's going on in the group 1 separation and the specific test associated with group 1s. So you should have an idea of the chemistry that's taking place and the chemical equations that describe the chemical reactions that take place. Remember, the key to doing well on the qual scheme is being very detailed and not cross-contaminating your samples. And if you have additional questions, please ask your lab instructor.